Hello, my name is Megan Walter. I'm a junior at the University of Oregon studying math and computer science. And this summer, I was given the opportunity to participate in the University of Arizona's CAT Vehicle REU. I got to work with autonomous vehicles, machine learning models, and simulation software. Now, due to the pandemic, everyone was working on their projects separately from home. But with my partner, Iris, from Washington State University, and our graduate mentor, Rahul, I was still able to learn a lot and gain a lot of experience, even while working remotely. For our project, we used recurrent neural networks in the Python TensorFlow Keras library to model an individual's driving behavior using a car-following model. That is to say, given an ego car, a car that we were controlling, and a lead car, a car that our ego car was following, our model took in three parameters: the ego car's velocity, the ego car's acceleration, and the lead vehicle's distance from the ego car. And using this information, the model output a change in velocity, or delta v, that we could add to the car's current velocity to determine its next velocity. Due to its nature as a recurrent neural network, the model would look at a history of the last 100 values for each parameter and use that information to predict a reasonable next point in the trajectory. Thus, we added the current velocity to the history that the model would predict the next point off of. My role in the project focused mainly on transfer learning in a simulated environment. To do this, I used a combination of ROS, standing for Robot Operating System, a visualizer called Gazebo, and the CAT Vehicle Simulator. We set up the ego car and the lead vehicle in the simulation. The ego car had a laser sensor activated so that if the lead vehicle was in range, it would be able to compute the lead distance. Because we had to make the lead vehicle move for the model to work properly, I took data from a trip that had been recorded by our data collection vehicle and had the lead vehicle run that trip. As the lead car often moved out of range of the ego car's sensor, causing problems with the model's input, I reduced the velocity of the trip by a constant factor so that we could get a better understanding of the actual happenings of our tests. The model acted as controller for the velocity of the ego car. We fed the model the ego car's velocity and lead distance, allowing the model to create a new prediction, which, as I explained earlier, would then get published to the car and added to the history on which the model could look back on. This allowed the model to create an original trajectory based on the patterns of the data that we trained it on. While our initial few iterations of the model had slight issues with primarily very small and/or negative velocities being predicted, the later models showed marked improvement as we filtered and optimized the data that we trained the model on. I very much appreciate my experience at the CAT Vehicle Research Program. Even with the limitations of our current predicament, I was still able to grow so much, not only in my knowledge, but as a learner and as a collaborator. This is my first experience with machine learning and formal research, and I am so grateful for the opportunity to both dive into and learn about the process of both of them.